Good evening and welcome to the Spring 2023 Fellows Colloquium. I'm going to go ahead and give everyone just a couple of minutes to arrive, but while we're doing that, I just want to say hello and welcome. My name is Catherine Halsey, and I'm with the Development Office here in the College of Natural Sciences and Mathematics, and I'm excited to be facilitating this Fellows webinar today. So just to let you know, this is a live session, but your camera, your microphone, and your chat functions have all been disabled. If you have any issues this evening, please let us know by emailing us at cnsm-fellows@csulb.edu. And also just to call your attention, after the presentation, we're going to have a Q&A session towards the end of the webinar, where Dr. Tian will be answering some of the questions that you may have. And then following the Q&A, we will then have a more informal opportunity for you to have a meet and greet for those of you who hopefully will be staying with us for the rest of the evening. And you'll be invited at that point to turn your camera and mics on and say hello to us. So during the session this evening, you are free to put your questions into the Q&A, which is a box located along the bottom of the Zoom interface. And throughout the presentation, you are welcome to go ahead and submit your questions, or you can hold them until the end, whichever you prefer. And also just to let you know, the presentation this evening is being recorded, so that way we can share this out with folks far and wide. So thank you again so much for joining us tonight, and we will begin with Dr. Curtis Bennett, the Richard D. Green Dean of the College of Natural Sciences and Mathematics.
Great, thank you so much. And welcome everybody to the Spring 2023 Fellows Colloquium. It's my pleasure to host this event. Our last one was also held virtually just about a year ago. So it's great to have everyone back again, and I'm delighted to be here with all of you. The Fellows of the College of Natural Sciences and Mathematics are individuals and companies who provide support for students and programs in math and science here at California State University, Long Beach. As fellows, they ensure that outstanding teaching and research programs are available to educate the next generation of scientists and mathematicians, as well as a science-literate citizenry. It's especially meaningful tonight to have fellows members John Leonard in the audience today, as he helped provide the startup funding for Dr. Tian's research lab, which has opened up so many wonderful opportunities for our students. Thank you so much, John. I would also like to say hello and give welcome to Rob Friedrich and Sharon Houston, who have also been fellows members and friends of the college for several years. Rob and Sharon made the decision to become legacy donors, and we are really grateful to them for that level of support. So now it's my pleasure to introduce Dr. Li-Xuan Li, chair of our chemistry and biochemistry department, who will introduce tonight's speaker, Dr. Fangyuan Tian.
Thank you, Dean Bennett. It is my great pleasure to introduce today's speaker, Dr. Fangyuan Tian. Dr. Tian is an associate professor in the Department of Chemistry and Biochemistry. She was born and raised in China and received her BS degree in polymer chemistry from Jilin University in 2008. She received her PhD in analytical chemistry at the University of Delaware and completed her postdoctoral work at University of San Diego. Dr. Tian joined CSULB as assistant professor in 2015 and was promoted to associate professor in 2021. Dr. Tian teaches instrumental methods of analysis, quantitative analysis, materials science, and surface chemistry classes. Dr. Tian's lab has a broad research interest in the disciplinary area of surface materials chemistry, with a focus on environmental and biomedical related questions. Specifically, she studies the fundamental properties and chemical reactivities of nanostructured solid hybrid materials for applications in greenhouse gas capture, photocurrent conversion, water remediation, and drug delivery. Dr. Tian is a proud beach mentor. She has mentored over 30 undergraduates and 10 graduate students since 2015. Her awards and honor includes 2016 Environmental Research and Education Foundation Research Award, 2018 American Chemical Society Petroleum Research Fund Undergraduate New Investigator Grant Award, 2020 CSULB Earlier Academic Career Excellence Award, 2020 NIH SCORE Grant Award, and 2022 NSF Career Grant Award. Now, Dr. Tian lives in Long Beach with her husband, 1-year-old son, and 4 cats. In her spare time, she likes reading, cooking, and watch movies. She told me that she has been reading Colin Hoover's Never Never and Stephen King's Fairy Tale this week. Dr. Tian.
Well, thank you so much. Thanks for the introduction, Dr. Lee and Dean Bennett. It's my great pleasure to be here today. And let me start sharing my screen. Yeah, I've been reading those 2 books this week, but I already finished that Never Never, but it wasn't a very good book. So I would recommend never pick up that book. Well, let me just pull out the laser pointer. Well, thank you so much, everyone, for coming today to the Fellows Colloquium talk. So today's talk, I'll highlight some research that have been done in my group in the past 7 or 8 years. So all the work I'm going to talk about today, they are done by those amazing students. I've been fortunate to have lots of talented undergrad students and master students, and this is our current group. I think we're missing 3 people here. So let's get started. So one of the pictures I showed in the previous slide, it was taken on the beach of just Long Beach next to the pier. And I hope you enjoyed. I think many of you have walked on that beach. It was a pretty amazing view. And some of you probably noticed we have lots of those small islands, those artificial islands. Those are those oil rigs islands. And when I checked today, and I realized those islands, they have name. They call the Thumb Islands. It was very interesting. But if you look at those oil rigs at night, sometimes you will see the fire, and especially in the complete dark condition, it looks like the fire, they're floating in the sky, and those are from the methane. So those are the methane fires. Just because we have too much methane being generated from those oil rigs, and they can't transport it directly back to the shore. So for the safety reason, they have to burn it. Apparently, this is such a waste because methane, it is it's the primary component in natural gas, and natural gas, we can use it as an energy. And if you look at this table, and we found that methane is roughly delivers around twice of the energy compared to coal in terms of the amount of carbon dioxide has been released. And based on the EPA data, we noticed that the natural gas and petroleum systems together with the landfills, they will take up to almost 50% of the human-related methane emission every year. And we can use those type of methane that is released to the atmosphere as an energy. Especially methane is a greenhouse gas, and we're trying to minimize the emission of it. So it's much simpler to purify the methane out of those oil rigs, because those are just pure methane coming out compared to the landfills. The landfills has a mixture of methane and carbon dioxide, especially at the phase 4 when the landfill is mature, and it's about 50% of methane and almost 50% of carbon dioxide mixed together with some impurity gases, including oxygen, nitrogen, and lots of water. So it's much more difficult to purify methane or extract methane from a mixture of different gases. But if we could use those methane, so we can convert those waste to energy, and you basically need nothing from the landfill, so it's free, and we can generate much more economic benefits. all the available techniques so far for purifying landfill gas. So we could use chemical, water means scrubbing, or the physical distillation, depending on the boiling point difference in methane and carbon dioxide, or the membrane separation or molecular sieve methods. But all of these techniques, they have their own drawbacks. And if you look at some newer research, you found that there are some good and more efficient absorbents to solve this problem. So when we look at the literature, and we found out that there's a type of materials known as the zeolitic imidazole frameworks. Those are highly porous. All of those, the yellow balls you look at on those figures, that represents the empty space. So this type of material, you could understand this as our building. Just imagine Hall of Science or any other building, you have different floors, and on each floor, you have individual rooms. And those empty rooms can be used for trapping gases or other gas molecules. And in this study, at the very beginning, we started with a type of ZIF. It's called the ZIF-8. It is composed of zinc ions connected by 2-methylimidazole and forming this solid-like structure. And it has extremely high surface area, almost around 2,000 meters square per gram, and a large pore volume. More importantly, it has a relatively stable thermal stability. So, and when you look at the pore size of this type of material, it's around 3.4 angstrom. So it is close to carbon dioxide. So we're thinking that maybe you can use this type of material to trap carbon dioxide and free up methane. So this is just a closer look of the ZIF-8. Why it's called the zeolitic imidazole framework is just because the metal, imidazole metal angle is similar to the zeolite. So in our lab, we synthesized ZIF-8 nanocrystals using a rapid method at room temperature. So after synthesizing these in ethanol, you notice that all of these particles, they're around 100 nanometers. And this work has been done by Benjamin Dow. He is an undergrad student in my lab. And later on, we found that if we change the ratio between zinc and 2-methylimidazole, we can adjust the particle size and change the morphology of it with a higher ratio or a higher amount of 2-methylimidazole linkers. And all of those particles, they would just aggregate together. So we could tune the size and the morphology of that. But when we look at the carbon dioxide absorption amount, we found that ZIF-8, it can absorb lots of carbon dioxide. So it's around like 10 millimole per gram of ZIF-8. But for this type of carbon dioxide trapping or absorption, we have to do this measurement at 90 Kelvin. So that means this material is only effective for trapping carbon dioxide at extremely low temperature condition. But for those landfill and the petroleum, natural gas systems, we usually handle those gases around room temperature. So this is not very practical. We go back to this table and look at the whole ZIF family. And this time we noticed a type of compound known as the ZIF-95. ZIF-95 has a similar but more complicated structure. It has a larger pore. And if you look at the aperture is around 3.65 angstrom. This value is important. It's just because when we look at all of the different gas molecules, so carbon dioxide is around 3.4 angstrom. The kinetic diameter of carbon dioxide is 3.4 angstrom. Oxygen is like the bigger. Nitrogen is around 3.6 angstrom. And methane, that's the biggest one. So that's around 3.8 angstrom. We're thinking if we could find a type of porous material with the aperture around 3.7 angstrom, so that means those impurity gases can enter, so they can be trapped there, except methane. So this is like a funnel, or it's just based on the molecular sieving process. So we can use type of ZIF-95, which has a approximately 3.7 angstrom per aperture to trap all of these gas molecules. But the reason we want to add a little bit zeolite 4A is the zeolite 4A, this is a natural compound. You can find it in nature. And this could function as a seed to promote the nucleation process of CYP95. And when you compare the size of CYP95 with and without the zeolite 4A, you will notice that the zeolite has a great functionality, and it can trigger this crystal grow, and the crystal will be much bigger. And the CYP95 will show like the layered structure. So we can use that for carbon dioxide trapping. So my student, Melissa Young, she performed lots of those nitrogen absorption analysis. And this time we found this hybrid material, the zeolite at CYP95, it has a pretty good carbon dioxide absorbing amount, even at room temperature, so at 298 Kelvin. And we noticed that the QST value, which is the heat of absorption, is relatively low. It's only between 20 to 30 kilojoule per mole. So this value indicating that the zeolite at CYP95 hybrid material, so this is a physisorption process for carbon dioxide. So it'll be much easier to regenerate. So for any chemabsorption process, this value could go up to around 100 kilojoule per mole. Another student in my lab, Jack Eldridge, he did the computational work based on the ideal absorbed solution theory, or IAST, to figure out the selectivity of this type of material toward carbon dioxide and methane. And we noticed that for the hybrid material, even at room temperature, the selectivity can go up around 16. So that means every 16 molecules of carbon dioxide being trapped in the pore, there's only a single methane molecule could enter. So this is a pretty good selectivity. That means we can use this hybrid material to purify methane from the landfill gas, even at room temperature. So it's much better compared to CYP8. But when we go back and look at CYP8, and we're trying to figure out what can we use the CYP8 for? And because of the easy synthesis of CYP8 in the ambient condition, just using a pretty simple solvent, we decided to try it out and see if we can use it for water remediation. So we started with the same type of CYP8 nanocrystals. And this time we used Romin B as an example, as the organic dye contaminant in water. So it has this beautiful pink color. And when we placed the CYP8 nanocrystals in there, even stirring it with light, without light. So after, you can see that even in the dark condition, after 30 minutes, all of those pink dye will be gone. And for the UV condition, even after 10 minutes, and the pink color will be gone. And we're trying to figure out what is the mechanism for this CYP8 absorbing of Romin B. So based on our studies, we found that at the dark condition, CYP8 has lots of functional groups on the surface, and those groups including carboxylate, the carbonates, hydroxide, and secondary amine, they could absorb or trapping those Romin B on the surface have a stronger interaction. When we expose those material with light, with a visible light, and we notice that it will trigger this stronger absorption process to initiate a better binding between the CYP8 and the Romin B. Under the UV condition, we use a terephthalic acid as a probe. We found that CYP8 could generate those hydroxyl radicals under UV condition, and those hydroxyl groups, it will attack those Romin B and to decompose those organic contaminants in water. So after that, we're thinking, because it still will take about 10 minutes even under the UV condition. Can we make this water filtration process faster? And this time we're thinking, if we're building a membrane with this type of CYP8, it could move the water much faster in the flow. So my graduate student, Ricky Rodriguez, he started with this electrodeposition process of building zephate on a stainless steel mesh. So he started with directly building the zephate on top of the stainless steel mesh, but it didn't work. So he found out we need 2 steps. The first step is to attach a zinc plating on top of the stainless steel mesh. And then he could incorporate the zephate directly on top of the zinc. But we're thinking, if we could just remove those organic contaminants, is it possible we could add more functions to this membrane? So we designed a silver-containing zephate because the silver, it is a type of material, is antimicrobial, and it could interfere the DNA replication or denature the protein inside of those bacteria. So in that case, we could have multifunction of a membrane. This is how the surface looked like. This is a bare stainless steel mesh. It looks very smoothly on the surface, not too many features. After the zinc plating, you can see that we have a interesting layered structure, and we found out this is a zinc nitric hydroxide crystal. Even after 10 minutes, we could have like pretty thick coating on top of the stainless steel mesh. And once we add the zephate solution and repeat this electrodeposition, you'll notice there are lots of zephate particles have been coated on the surface. And with the silver zephate system, it doesn't look quite differently from the zephate, but when we compare the the EDS, the elemental analysis, we notice that there's silver all over the surface. So you can see this is the picture showing the silver elements in the blue color. And when we compare the performance of the zephate and silver incorporated zephate membrane, we found that in both cases, the absorption for Robin B is similar, but you can see that for the silver incorporated zephate coated stainless steel mesh, it has a very strong antimicrobial property. So almost 90% of the bacteria, we use E. coli, and then all the E. coli, it died. And this, the E. coli culture growth study was done in Dr. Banderi's lab. Some key conclusions for the first part of my talk is we look at a family of zeolated imidazole framework, and we come up with those hybrid zeolite with ZIF materials. So compared to the parent materials, it has a much higher efficiency and lower cost to absorb carbon dioxide at room temperature. And then for the other type of ZIF, the ZIF-8, we can use it for water remediation, can remove organic matters, and we could also build it on the stainless steel mesh as a membrane using a super simple method. Will only take about 10 minutes. All right, so now I'm going to switch the gear a little bit and talk about the drug delivery project in my lab. So some of you probably know about this coronary artery disease, and this is the #1 cause of death in the US. So this is a healthy artery. If you look at the cross section of it, you will notice it has a smooth layer of the endothelium cell layers. And but this layer can be damaged by many things. For example, the toxins from cigarette smoking or too much fat food. And those cholesterol can be attracted to those injured area. So in that case, we'll have some plaque build up inside of the artery. And once those cholesterol starts oxidizing, our body will sense that. So our body, the immune system, will send out those monocytes. And now those monocytes will become macrophages. The macrophages means they will start eating those cholesterol trapped here. But let's say if the cholesterol is too much and those macrophages couldn't finish eating it, so they will die from eating too much. And in this case, they will accumulating together with the cholesterol and become foam cells. And because those macrophages have calcium inside, and when they die, they will release the calcium out. That will make this part of the artery become hard and brittle. So it's easy to be ruptured. The patients who suffer from this, very likely 50% of the patients will go through this balloon angioplasty surgery with a stent planted inside of their artery. So this surgery was done through using a catheter, a balloon, and a stent. So the catheter will be inserted through the periphery arteries on the arms or the legs of the patients. And when they reach the injured area, the balloon will be inflated to expand this stent to push the plaque back. And after that, they will deflate the balloon, take it out with the catheter, but leaving the stent in the injured area. But our body don't like any external objects, so they tend to reject it. So all those endothelium cells will regrow on top of the stent. So that could cause a secondary blockage. So the nowadays stent, so they have a coating for drugs that can be released after the balloon angioplasty surgery. So I have a model here. Let me just stop sharing my screen and I can show you very quick. All right, so this is a model I have. Oh, I probably shouldn't use the yellow background because it looks so similar to my model. All right, so this side is the healthy artery, and this side is the one that with lots of plaques. If you eat too much fries, and that's probably the artery will look like. And as you can see that all the blood cell, they will flow much faster on the healthy artery versus on this side, those blood cells will be trapped there. So the balloon angioplasty surgery will be insert the stent, expand it to restore the blood flow. Okay. All right, so I'll go back and share my screen. But as I mentioned, all of the currently available drug-eluting stent, so they have a layer of polymers, and those polymers, they're not biodegradable. So that means those polymer, it could have a chance that peeled off, especially for those young patients, if they have the stent being inserted into their artery for like 30 or 40 years. So they could cause stroke or other serious issues. So the newer version of drug-eluting stent will be to make it with a polymer-free material. So there are many different ways of doing that, including nanoparticles, self-assembled monolayer, or direct coating. But our lab specifically focusing on the parts inorganic coating. And we utilize a iron-containing metal organic framework. So the metal organic framework is made of those iron clusters connected by different organic linkers. So the good thing about using those MOFs is we could adjust the pore size. Let's say if you want to load a smaller drug, you can use a smaller linker. So we, for example, here we can use MIL-88A. Or let's say if you want to load the bigger drug, and you can use a longer ligand. Okay. Well, so far our group have been focusing on the MIL-88B. So it has a decent size, not too big or too small, and we have used ibuprofen as a model drug. But when we did the synthesis, we noticed that MIL-88B is not a material that is easy to be synthesized. You have to be very careful about the temperature. If the temperature is too high and you will not get MIL-ADB. Instead, you will the terephthalic acid and iron, it will go through a homogeneous nucleation, and this time you will get the MIL-53, which has a one-dimensional channel, versus MIL-ADB, it has a 3D channel, and it will have a preferred growth orientation on surface. But at the very beginning, we have no idea which one will be better, so we tried both. So my students, Kimberly and Hal, they did all of those experiments, and we found that for MIL-ADB, it can load around 20%, 28% of ibuprofen. Well, MIL-53, it has a much higher drug loading amount, so it's around 37%. But when we look at the drug releasing process, we found that it could go through different models. For example, the drug molecules, they will just release out from the framework without changing the structure. So this is known as the diffusion control releasing, or the material, it will start decomposing, but starting from the surface. So this is a surface erosion process. In that case, they should follow a Pappas model, or the crystal, it can break it down to smaller pieces and release drugs from itself. So that's known as the bulk erosion. And based on our results, we noticed that so both MIL-53 and MIL-ADB, it will go through all three together with a burst release at the very beginning, the first 6 hours, and after that, it will be relatively stable. But when you look at MIL-ADB, even after 10 days, and it's still around 20% of the drug just being released out. So there's still a lot of ibuprofen has been left inside of those pores. So we found that the drug releasing amount is actually related to the decomposing of our material. So a quick comparison between those two materials, they could be synthesized through either a homogeneous or heterogeneous nucleation. MIL-53, because of the one-dimensional channel, although it has a higher drug loading amount, but it will also release the drugs much faster compared to MIL-ADB. So MIL-ADB has a controlled drug releasing up to 10 days. So we decided to go with MIL-ADB and functionalize it directly on the surface and see if it would be potentially used as a drug-eluting stent coating. We started with a gold surface because it's chemically pretty inert and simple. So we can use a thiol-containing self-assembled monolayer to modify the surface. And because of the carboxylate groups on top of the sand, and we can directly connect it to our MIL-ADB crystals. And after that, we'll do the drug loading and see how much drug can be loaded there and monitor the drug release process. My graduate student, Andy, he started this project, and we tried different methods of building this crystal directly on top of surface, but we found that the direct crystallization method, that's the best way of loading lots of different, the different amount of MIL-ADB on top. And then we confirmed the structure of our MIL-ADB, so that is the rate crystal structure. So Angela, she worked in my lab as an undergrad student, and she continued this project. She connected those MIL-ADB crystals to the modified gold surface, and he tested how much ibuprofen can be loaded there. And we found that after we use a PBS solution, and the majority of the MIL-ADB will be gone. So she used a quartz crystal microbalance to look at the drug loading amount. So we found after the crystallization, direct crystallization process, we have around 17 microgram per centimeter squared of material has been loaded on top of the gold sensor. And after exposed to ibuprofen, there's about 9% weight percent of ibuprofen being loaded to MIL-88, compared to 20% for the powder this drug loading amount is about like half of the ibuprofen less compared to the powder. So we believe that's because we have limited surface area. All of the crystals have been attached or fixed on top of gold. So that's why it caused a 9% drug loading amount. We also used scanning electron microscopy to look at the morphology of the surface after each modification step, starting from a self-assembled monolayer coated gold. So it's relatively smooth and flat. And after exposing the surface to MIL88B, you can see we have lots of crystals being attached to surface. And for each individual particle, so it's around 500 nanometers big. And even after drug loading process, majority of the crystal didn't change much. So that means the drug loading doesn't affect the structure or the morphology of MIL88. But after we expose the surface to PBS solution, and lots of those crystals, they were washed away or they start decomposing. But because our MIL88B is quite biodegradable, so we want to look at the pH responsiveness of this material and see if we can use it for drug delivery at different pH conditions. So my graduate student, Stephen, he did those experiments of using a surface plasma resonance microscopy to look at the MIL88B crystals under different pH conditions. So it's under a flow of the saline solution under different pH conditions. So this is the neutral condition. So we could monitor the dissociation rate by looking at how the surface will be changed. So this is the advantage of using a SPRN. So here we can look at the mapping of the whole surface. So this is about like pretty big, like 20 by 20 micrometer of a surface. So you can, you'll notice that with a higher, like a color of pink, that means we have more crystals there. So we summarize all of data here under the different pH conditions. We notice that in an more acidic condition, so the decomposing or the dissociation rate is about 10 times higher compared to neutral condition. And that's exactly what we observed for drug delivery using the QCM to look at the real-time or the in situ drug release process. So when the PBS solution at pH of 6.3, you'll notice that this dropping of mass or the frequency is much deeper, or it will drop like more drugs compared to the neutral condition. Continue with the work because gold is not a very practical surface. And now we move on to use a medical grade stainless steel. So it's a 316 stainless steel. And this is the material people use that for making those drug-eluting stents. And now we're repeating the same strategy, but this time we're using a different self-assembled monolayer with the phosphate end group to attach those MIL88B on top of the surface and for drug loading and releasing experiments. So this work has been done by my master's student, Lynn. So she's a very hardworking student in lab. So we have lots of great results from this part. And another undergrad student in my lab, Ethan and Angela, so they've been working on the electron deposition of MIL88B on stainless steel. So we're trying to get a layer of the MIL88B crystals on the stainless steel, so it will be a much faster process of attaching those crystals for drug delivery purpose. So we're trying to use the same strategy as what we did for Zifate on the stainless steel mesh, but this is still an ongoing project. All right, so to conclude this part, we have been starting the iron-containing metal organic frameworks for drug delivery, and hopefully we can use it as a drug-eluting stent coating. Based on our findings, we noticed that MIL-88B has a relatively low drug loading amount. It's 28% compared to MIL-53, but it has a more sustainable release compared to the other one. And we have been starting this type of material on different surfaces, including gold and medical grade stainless steel. So hopefully we can improve the drug loading amount of the surface supportive MIL-88B on stainless steel. So this is just part of what we do in the lab. And our lab has been focusing on the surface and interface chemistry of a type of porous material, the metal organic frameworks. Today, I only talk about the biodegradable iron-containing methane films for drug delivery, and some of the work we did for the carbon dioxide, methane separation, and water remediation. There's another project I didn't get a chance to talk about it, but I do want to highlight that Christy Ashihara. So she was a master's student in my lab. She already graduated, and she started this project. And Raymond and Tiffany, they've been working on a fluorescence MOFs project. And so this is also a brand new project, and I didn't get a chance to talk about that today. Yeah, well, so I would like to thank all my students. As Dr. Lee has already mentioned, I'm a very proud Beach mentor, being fortunate to have lots of great students working in my lab. And I realized this is, I'm not just a research mentor or advisor for them. I'm actually providing experience for them to enjoy during their, no matter if it's undergrad or the graduate, those time at Cal State Long Beach. So I've been, very lucky and happy working with all my students. I do want to highlight the John and Elizabeth Leonard Family Foundation, this support, because Dr. John Leonard, he actually gave me some startup money, and without his help, I couldn't, recruit so many great students and eventually get other grant support later on. So thank you, thank you so much, Dr. Leonard. I would also like to thank all my collaborators, Drs. Lowinska, Bandari, Bu, Tepovica, and Sean from our chemistry department, and Dr. Kwong, Gradek, and Gu from physics. They helped me with some AFM images, and Dr. Wang from Cal State LA, the chemistry department. We've been working together on the SPRN, and this is my current group. And so I would like to thank you for your attention, and I'm happy to answer any questions you may have.
Thank you, Dr. Tian, for this wonderful presentation. Now we have questions and answer open. That you can use your Q&A, type in your question. I guess while we're waiting for a few questions coming in, I can start asking you a couple of questions. Now, I noticed you use both gold and iron in your MOF materials. So what is the consideration of using iron-containing MOF?
Yeah, so for those iron-containing MOFs, they have a relatively low toxicity. And actually, I don't have the data here, but Dr. Swinska and her student, they helped us with the cell studies. So they noticed that the IC50 value is relatively high for those MIL-88B crystals. Or let me see if I can find that slide. Yeah, well, so it's basically it's just the low toxicity for those iron-containing moth. And if you look at some of these mill materials, for example, like this one, the mill 88A, this ligand is the supplement people usually take, especially for those pregnant women. They take it for the iron supplement during pregnancy, so it's very safe.
Great, thank you.
Thank you so much, Dr. Tian. I have a question.
Sure.
I was excited to see how many of the projects had students on them. Can you talk about where a couple of the students are today and what your research has helped them go off to do?
Oh, of course. Sorry about that. I'm recovering from a cold from my son. He just started daycare and then I got all the viruses. Well, yeah, I didn't get a chance to talk about that, but our lab, about 50% of the students, they will enter industry, and 50% they will go to a professional school, such as PhD, MD, or pharmacy professional schools. I want to highlight a few students here. Most of our undergrad students, if they go to a PhD program, they prefer a UC. The other day when I was checking, I realized that we send our students to almost all the UCs. That's pretty amazing. And but we do have a few students, they go out of state. For example, Mark. So he is a PhD student at Georgia Tech, and I think he's on his 4th year already. And then I have a few students, they went to UCI in their biochemistry and material science programs. Michael. Oh, sorry about that. Yeah, so Michael, so he is a PhD student at UC Santa Barbara right now. And Hal, he went to UC Berkeley. That's the first student in my lab who went to UC Berkeley. And then some of the work I introduced today was conducted by this amazing student, Benjamin Dow. He's still in my lab. Now he's currently in the gap year. So he works in my lab as a lab technician, but he has already been accepted into so many PhD programs, but he decided to go to UCSD. So he will be there in the fall. Yeah, but we do have lots of students who directly go to industry. Yeah, so those students are also amazing. Also, the first graduate student I have in the lab, Andy, he is currently a tenure track faculty at the DuPage College in Chicago. Yeah, so I think, our lab alumni, they're pretty successful. And thank you so much to all the donors for your support to our students.
I got a couple of questions from Q&A. One question from Andy is for, he asked for the CO2 capture Z-Light. Can this be scaled up in industry?
Yeah, well, I hope so. But we didn't apply any patent for that. But this is a pretty good material compared to the current available absorbent. So one thing I didn't talk about is the current available absorbent. So they are titanium dioxide based, and those materials, they're super sensitive to water. So that's why you will have like several different tanks, and each tank contains about 1 ton of those zeolite. And you will have to remove water before introduce it to this absorbent. But for our material, it is super stable in water conditions, so you could expose it directly to everything. The cost of it is much cheaper compared to this titanium dioxide based zeolite, because we added zeolite 4A in there, so it can decrease the cost to I think I have the number in the paper, but it's not on top of my head, but they decreased the cost to only 1/6 of producing the pure ZIF-95. Yeah, so I hope one day they can be put into those big tanks like these.
Thank you, Dr. Tian. There's another question from Saba. She's wondering how easy it is to separate zeolite from water after filtering the contaminants.
Okay, so how easily to remove water?
To remove your zeolite.
Yes, so that's a question about regeneration, right? So as I mentioned that those zeolite materials, they are pretty stable in the in the moisture condition, and we use those zeolites as the those absorbent for water in lots of chemical reactions, and we have like a big 10 of those dry red. So those are and also those the molecular sieves, those round white molecular sieves. You probably use it in organic chemistry before. You can just easily heat it up, and then the water will be gone. And if you look at the QST value for our material, because this QST value is relatively low for both carbon dioxide and water. So you can just simply heat it up, and then the water will become vapor and leave the surface and from inside of the pores, and then you can reuse it.
Here's another question from Raymond. He's asking, is it possible to directly convert the captured CO2 in the spent zeolite 8 into methane or methanol?
Oh, yes. That's a really good question. There are people, they're trying to directly convert methane to methanol. So this is like a oxidation project, because methane is a gas, is difficult to transport, especially in those the petroleum and natural gas field. And they will prefer to convert it to methanol, which is a liquid, and that will be much easier to transport it. But the problem is, usually for methane methanol conversion, you will need a strong acid, typically sulfuric acid, and heat it up to a high temperature and use palladium or platinum as a catalyst. So right now, people have been thinking about using the copper maldanite, which is a zeolite, to convert methane to methanol directly, because they think there's some active sites inside of the zeolites. It will work. It is quite difficult to add this maldanite site, that's a reactive site, to ZIF-8, because ZIF-8 is a zinc-containing moth. You may consider using a copper-containing moth. So if you have this copper, oxygen copper that bound, so it's mimicking this the maldanite structure, you may be able to convert methane directly to methanol, but you may still have like a super high temperature requirement, at least around 200 Celsius. But this is like the superheated area, the research area, lots of people are looking at. Mm-hmm.
Thank you. Here's another question from Jim. What do you do with the absorbent material when it becomes saturated and it becomes less effective?
Mm-hmm. Yeah, so this is the, this is a problem that lots of materials will face. And once they've been saturated with carbon dioxide or impurity gases, we'll have to regenerate it. So that's why we have to heat up the material. But luckily, because of the low QST value, you don't need to heat up to a super high temperature. You can just heat it up to maybe around 50 Celsius. So in that case, all of the gases will leave from the pores, and you can collect all of those trapped materials, for example, carbon dioxide, and then to pump it into their, usually we use a reservoir, it's a CO2 reservoir underground, and those CO2 will be converted to coal like in 1,000 years, so people can reuse it. Yeah. So you just use the thermal energy to regenerate the surface, to regenerate the material, to get rid of those saturated impurities.
Are there any more questions from audience? If not, I guess that concludes the question and answer. Turn the floor back to Dean Bennett.
Thank you, Dr. Tian and Dr. Lee. As I mentioned earlier, the work that our faculty and students are doing would not be possible without your support. So I invite you to consider partnering with us to continue creating opportunities for our students to participate in faculty research labs. And as you heard, that participation in the labs means that they go on to do great things that, you know, and I know Dr. Tian spent most of her time talking about her students who are in academia, but remember, she also said 50% also go off and work and research in the area. So if you're worried about getting them out into research in the area just as much as you're worried about getting them to graduate programs, this is the sort of thing to help us with. So I really want to emphasize. And so if you want to support these opportunities in chemistry and biochemistry or any other department, we've included an online giving link in the chat for your convenience. I also want to let you know about another event taking place here in the college, which is the annual prize lecture, which is being organized as usual by our CNSM Student Council with guest speaker, Dr. Andrew Knoll of Harvard University, the recipient of this year's Crawford Prize in Geosciences. The Crawford Prize, for those of you who don't know, and I didn't, is the Nobel for the non-Nobel Prize categories given out by exactly the same institute. So it is effectively the Nobel Prize in areas that don't have Nobel Prizes, and geosciences is one of those areas. That event is taking place on Tuesday, April 25th, starting at 9:30 a.m. for the general lecture in our university ballroom. And there's also a way to attend virtually. Please, please, please keep your eye out for a follow-up email with more information about this event, or visit the website, also noted on the slide and in the chat.